Hello friends, I am Amirun Nizami and today we are going to study the linear second order ordinary differential equations using variation of parameters and the power series solution. So last time we have studied this second order ordinary differential equation using the undetermined coefficient methods, and that method was only applicable when there were some special functions, and those special functions we have talked about, that those special functions were e to the power mx, sin mx, or cos mx, and x to the power n. These were the special functions. When in equations we have written y double prime plus p of x y prime plus q of x into y is equals to, so when we were using in the examples we were using a constant, so we may use here 2a we have used, and here we have used as constant b, a and b, by, that is equals to these special functions, a special function. So we have easily solved these problems with constant coefficients and the special functions using the undetermined coefficient methods. Okay, but now when the coefficient, when the special when the functions functions are not spatial, are not spatial, that is fx is this function and any other function such as sec x, tan x, or any other function of x, then we have to use the variation of parameters. Then we have to use we have to use methods of variation of parameters, variation of parameters. Okay, so when there is any y double prime plus, we can say p of x of y prime plus q of x equals to f of x, then at that point of time we have a homogeneous solution and a particular solution. So when we know the homogeneous solution, like when it was a constant, then we use generally c1. For this constant we can see y homogeneous equals to c1 u1 of x plus c2 u2 of x. Okay, then yp at that point of time was g1 of x into u1 of x plus g2 of x into u2 of x. We consider this yp as just replacing c1 constant with the g1x and c2 with the g2x, and u1x and u2x are same. So we just use this method. If y of h in homogeneous solutions are known to us, then and only then we can find out the particular solution when we are using the methods of variation of parameters. So when the coefficients were constant, then the homogeneous solution was easy to find. But when coefficients are are not constant, but a function of x, a function of x, then we have to find the homogeneous solution, homogeneous solution using power series method, power series method. So what this state, that y double prime plus p of x of y prime plus q of x of y is equals to any function. So when we are solving this as a Ly is equals to 0 means homogeneous solution where px and qx are non-constant or function of x, then this can only be solved with the help of a power series method, that we can get the y of h. Okay, so to find y of h we have to use this power series method. So let's find out. Let us see one example. Let's take example 1, y double prime plus y is equals to 0. Hence these are the constant coefficients and we have solved these solutions. But even though we are considering this first using the power series method, and then we will use the um, function of x to solve the another problems. So let us take this equation as 1. So these are the constant coefficients with p of x is 0, constant coefficients here with p of x equals 0 and q of x equals to 1. Okay, so now for solving this problem, let us assume that our solution has the form of power series such as y is equals to n 0 to infinity a n x to the power n, that is equals to a naught plus a1x plus a2x square plus so on. And y prime would be, so if we differentiate it, what it would be, n equals to a, n would become outside, just a minute, sorry, n into a n into x to the power n minus 1. That is, when we differentiate it we will not have a naught, so we will directly have a1 plus 2a2x plus so on. So we can say that it will start from a1, so now it would be n equals to 1 to infinity, and then we have double prime, that is n. So when we will solve it and we will differentiate n into n minus 1 an x to the power n minus 2. So n is equals to, we can say if we differentiate it, so it would start from 2a2 plus so on. So it will start from 2 to infinity. Okay, so now we replace all these equation 2. So substituting equation 2 in equation 1, back in equation 1. So what will happen? We will see that instead of phi double prime n equals to 2 to infinity n into n minus 1 an x to the power n minus 2 plus n is equals to 0 to infinity an x to the power n, that should be equals to 0. So now we will use the property. What is the property? That summation of n is equals to 0 to infinity an is equals to summation n equals to k to infinity a of n minus k. So just replacing n equals to 0 to infinity an, that n equals to k to an minus k to infinity. This is the property we will use here in this equation. So now we will make this from 0. So we will use this property as n is equals to 0 to infinity. Replace n with n plus 2. So n plus 2 into n plus 2 minus 1. So n plus 1 into a of n plus 2 into x to the power n plus 2 minus 2. So x to the power n plus, this is the same, n 0 to infinity n x to the power n is equals to 0. So we can take n is equals to 0 to infinity, and we will solve n plus 2 n plus 1 into an plus 2, it was an plus 2, and this coefficient was plus of an into x to the power n is equals to 0. So for that, this must be equals to 0. N plus 2 into n plus 1 into a of n plus 2 plus a of n is equals to 0. Therefore a of n plus 2 is nothing but equals to minus of a of n upon n plus 2 into n plus 1. So therefore if n is 1 or 2, then pick, you can pick a0 and a1 arbitrarily. Then for n is equals to 0, an plus 2 a2 will be equals to minus of a0 by 2 into 1, which is minus a0 by 2 factorial. N is equals to 2, a4 is equals to minus of a2 upon 4 into 3 a0 upon 2 into 3 into 4. So a0 by 4 factorial. N equals to 4, a6 would be equals to minus of a4 by 6 into 5, minus a0 upon 4 factorial into 1 by 6 into 5. 6 into 5 into 4 factorial, that would be minus of a0 by 6 factorial. Similarly, when n is equals to 1, we solve a3 is equals to minus a1 by 3 into 6, minus a1 by 3 factorial. N is equals to 3, a5 would be equals to minus a3 upon 5 into 4 is equals to minus of a3 is minus of a1 by 3 factorial into 1 by 5 into 4, that is equals to a1 upon 5 factorial, and so on. So we can finally write y is equals to a naught plus a1x plus a2x square plus so on. So therefore we can just separate a naught plus a2x square plus a4x to the power 4 plus so on, plus another in terms of one a1x plus a3 x cube plus a5 x to the power 5 plus so on. So then it is a naught into 1 minus x square by 2 factorial plus x to the power 4 upon 4 factorial minus x to the power 6 upon 6 factorial plus x to the power 8 upon 8 factorial minus so on, plus a1 times x minus x cubed by 3 factorial plus x to the power 5 upon 5 factorial minus x to the power 7 upon 7 factorial and plus so on. So we know that these are the expansions, power series expansion for a naught cos of x, plus these are the expansions for sine of x. So we get a naught cos of x plus a1 sine of x, and we know that the solution for this problem is this a naught cos x. So hence we were just cross checking our solution by using the power series method. But in the next problem which we are going to see is only possible by using this power series method. That is example 2, which is y double prime plus x of y is equals to 0. So here the function means coefficient is a function of x, and we know that other than the constant coefficients, if the coefficient is function of x, then we can only solve with the help of power series solution. And now the power series solution, we know here that we will assume a solution as 0 to infinity a n x to the power n, y prime we have already noted, 1 to infinity a n n into x to the power n minus 1, y double prime is equals to n 2 to infinity n into a n to n minus 1 into x to the power n minus 2. Okay, so we can say these are the equation 2. Substituting equation 2 in equation 1, let us substitute y double prime, that is we can say n is equals to 2 to infinity n into n minus 1 into a n into x to the power n minus 2 plus x into y. Y is in rather 0 to infinity a n x to the power n, that is equals to 0. So now we can take this x and enter inside. So therefore we can write n is equals to 2 to infinity n into n minus 1 a n x to the power n minus 2 plus n is equals to 0 to infinity a n x to the power n plus 1 equals to 0. So now this is n plus 1 and it is n minus 2. So here the difference is of, so we can replace n as n minus 3 here. So let's see. N is equals to 2 to infinity n n minus 1 a n x to the power n minus 2 plus Now this solution can be written as n is equals to 3 to infinity a n minus 3 x to the power n minus 3 plus 1, that is n minus 2, is equals to 0. Okay, so now we can consider n is equals to 2 to infinity a n into n minus 1 x to the power n minus 2 plus n is equals to 3 to infinity a n minus 3 x to the power n minus 2 is equals to 0. Now we can have this n equals to 2 if we put n equals to 2 to a2 into 2 into 2 minus 1, that is 1 into x to the power 2 minus 2 1. So 2 into a2 plus we can write it here n equals to 3 to infinity a n of n into n minus 1 x to the power minus 2 plus n equals to 3 to infinity a n minus 3 x to the power n minus 2 is equals to 0. N equals to 3 to infinity a of n into n minus 1 into x to the power n minus 2 plus n equals to 3 to infinity a of n minus 3 x to the power n minus 2 is equals to 0. a7 is minus a4 upon 7 into 6. That is, if we replace in the term of minus a3, then it would be a1 upon 7 into 6 into 4 into 3. So here also we are missing 5, so it is not the factorial. Here also 6 into 5 into 3 into 2, 4 is not there, so therefore it's also not a factorial of 4. So, and before this, last slide we have seen that these were equals to 0, so therefore a2 must be equals to 0, and also this should be equals to 0, but x to the power n minus 2 can't be 0. So this states this an equals to this formula and a2 is equals to 0 from here. So now we have picked a0 and a4 at random, and we have solved it. So a7 we get in terms of a4, so a4 and a7. So now we are getting this problem in terms of a1, and also we have seen a of 5 is equals to minus of a2 upon 5 into 4, hence a2 is 0, so therefore it is 0, and also a8 would be minus of a5 upon 8 into 7, so hence a5 is also 0, so therefore a8 is 0. So finally we get y means a8 is equals to 0, also a11 is 0, also a14, and so on. So finally y would be equals to a0 plus a3x cube plus a6x to the power 6 plus so on, plus a1x plus a4x to the power 4 plus a7x to the power 7 plus so on, plus a2x square plus a5x to the power 5 plus a8x to the power 8 plus so on. So hence a2, a5, a8 all are 0, 0, because it can convert in terms of a2. So these are 0, so therefore we will replace it with 0. So remaining that part, so y is equals to, we can replace a3, a6 all in terms of a1. So a0 into 1 minus x cube upon 6 plus x to the power 6 upon 180 minus and so on, plus a1 into x minus x to the power 4 upon 12 plus x to the power 7 upon 504 minus so on. So final solution we get in terms of a power series solution. So a0 and a1 is the coefficient, it is a1 which is a coefficient, and this is the series here. So we get the solution for the differential equations, which is y double prime plus x of y is equals to 0. For this problem we get this solution y. So we can say that for the non-constant coefficient or the coefficient when it is a function of x, we can solve with the power series solution and we will get the homogeneous solution. So we get the homogeneous solution for this equation. So this is the homogeneous solution for this equation. So thank you.